Yo, what up, Sci Fam? It's your boy Nickel, and today we're going to look at balanced free body diagrams and unbalanced free body diagrams. We're going to compare and contrast them. So first, start with the title on your page, titling it Balanced versus Unbalanced Free Body Diagrams. The top half of our page will have our balanced free body diagrams, and the bottom half of our page will have the unbalanced free body diagrams. Now we will be drawing 3 free body diagrams for each of the different categories. So make sure that you have enough room for all this information. Here we go. Let's start in a position of balance. Let's start with our balanced free body diagrams. Now think about like a teeter-totter. If everything is balanced on a teeter-totter, then there is no motion. Even though you might be suspended up in the air in a teeter-totter, if everything is balanced, there is no motion. There is not any movement at all. So you could probably then assume how an unbalanced free body diagram will be different. So if it's unbalanced, and if I get a teeter-totter here, it's not going to stay flat. Instead, you're going to have some type of motion happening. One might be going up or down or whatever that might be, depending on how it's unbalanced. So unbalanced free body diagrams, there is motion. I'm going to draw some motion lines here to accentuate the motion that's happening. Now, if we zoom out a little bit, you can see I drew like a little dashed line there to separate the two, so that as we draw our pictures, our free body diagrams here, it doesn't clutter it too much. So feel free to do that. So let's begin with our first example. This one is like some sled dogs. Now imagine you're sitting here being pulled by these 4 dogs here. So if we're being pulled, then obviously there's going to be some motion. But let's imagine first, if we were just in the sled and the race had not yet started. So again, the first rule of drawing a free body diagram is that we represent all images, all situations with a box. We put a dot in it to show the forces acting on this object, and the box represents the object. This one let's title sled, because this is just the sled that's sitting on the ground. So you can imagine that this sled has a certain amount of weight in it, especially if the musher or the person directing the dogs is sitting in the sled. So there's the downward force, but that sled is not going to be falling through the ground. So there has to be an up force also that's opposite of the weight of the sled. So let's label these 2 arrows here. So the downward force is going to be the weight of the sled plus whoever else is in it. The upward force, though, is going to be support from the ground. So you can imagine if this sled was put on water, the upward arrow would not be as strong and the weight would go through the water. So when we have a balanced free body diagram, what that means is that when we compare these 2 arrows side by side, if I were to take the up arrow and place it right next to the down arrow, they would be equal in size and opposite in direction. One's up and one's down. So therefore we would say that this is balanced. And when it's balanced, there's no motion. Imagine a sled that's just sitting there. There are forces that are acting on the sled. One of them is the weight, and the other one is the force of the ground pushing back up on the sled so the sled doesn't go through the ground. But there's no motion, even though there's forces being applied to this object. All right, well, let's imagine then our situation, and the person starting the race, they drop their arm, and the dogs start barking and running and yipping, and yay, we start moving. So again, now we're going to show an example of a sled, or at least the sled dogs pulling the sled. So again, we're going to represent our sled with a box with a dot in the middle, because that's always what's going to represent our object. Okay, so in this situation now, we have the dogs that are pulling us ahead. Now there's a little bit of friction that will be involved here on the snow, but there's not very much friction. Also, the weight of the sled is still going to be affecting the sled. It still has some type of weight to it, but it's not going through the ground, so therefore there has to be an opposite force also going up. So let's review the names of these different forces, because whenever we draw a free body diagram, we need to label the arrows. You can't just leave it looking like this, because I wouldn't know if you understand what each arrow represents. So again, remember the green arrow is the pulling by the dogs. We could say the dogs pulling. The red arrow is the weight of the sled. So you can imagine if this was even bigger, then the dogs would have to pull harder and harder to overcome that weight. The backwards arrow is just the friction. And that could be like of the snow, because you can imagine if we were on grass, then the friction might be even larger. And then the up arrow, our purple arrow, is the force of the ground pushing up on the sled. So if we take all of these arrows then and put them side by side, the ground arrow and the weight arrow are equal in size and opposite in direction. So there's no motion in the up and down direction. Our friction arrow, which goes to the left, and our dog's pulling arrow, which goes to the right, are not balanced. These ones are unbalanced. So our example here would be an unbalanced free body diagram. And if I were to show you, the actual motion is happening here. This would be the forward motion, because it's the difference of the two arrows. There's no difference here in these arrows, so there's no motion in the up and down direction. There would only be this forward motion. That would be the only motion in this picture. And that would be good, because if you're being pulled by these dogs, you wouldn't want to be going anywhere but forward. All right, let's check out another example. Imagine you're this cat. Come on, you got it. Oh, okay. Well, this cat is trying hard. We gotta give this cat some credit for that. So let's draw a free body diagram first of this situation where the cat is stuck, and then this situation where it overcomes being stuck. Let's title this one The Stuck Cat. All right, so we'll draw a box with a dot in it to symbolize our object, which is the stuck cat. And in this one, we'll go ahead and show that that cat was trying hard, and it was pushing really hard in this direction. But that door was actually causing there to be so much friction that the amount of friction was in the opposite direction of the cat, and it was the same amount of force as the cat. The cat did not move. So let's label our arrows here. We'll call this the pulling cat. Or it could be the pushing, because maybe it was pushing, pulling, whichever one. Well, regardless, it was moving in that leftward direction. The backwards direction would be the friction of the door. And the door wasn't letting the cat get through because it wasn't pulling hard enough yet. And even as the cat tried to pull even harder, let's draw one more here to show something very interesting, is that even if the cat tried to pull harder than it did the first time, the door still had enough force that it still wasn't pulling hard enough. At some point, though, the cat overcame the friction of the door, the force of the friction of the door, and was able to escape. But in these two examples, even though the cat pulled harder, it actually meant that there was more friction that slowed it down and tried to stop it. So sometimes if you can't move something and you push harder and you still can't move it, it's just able to overcome that force. It has this weight that we call inertia, which means that it's hard to overcome. But in this example, it shows how in both of these cases, in the first one, the arrows were opposite in direction and equal in size. And in the second one, they were opposite in direction and equal in size. So in this example as well, this would be an example of a balanced free body diagram, because there's no extra arrows over here. There's nothing extra in either direction that would cause there to be any motion. So when we add up the arrows, they're balanced. Therefore, there was no motion because that was a stuck cat. Now, let's check out the unbalanced free body diagram. This is when the cat would finally get free. So let's call this one the free cat. Okay, so let's get our free body diagram, our box with a dot in it. And in this case, we can imagine, you know what, that cat did have some weight, and we didn't add it to the last diagrams, but let's add it this time. And let's label this the weight. But it wasn't falling through the floor because the floor had an upward force on the cat. And so we could say that this, let's just call it the ground. The ground or the door or the floor was pushing up just as hard as the cat's weight was pushing on the ground. And that's good because it wasn't moving up or down, but it was moving forward. And when it finally got enough force to move forward, it was able to overcome that backwards force of the door. So let's label these the door friction, and the forward arrow was the cat's pull. So now if we put these arrows next to each other, the ground was pushing up, the cat's weight was pushing down equally, so there was no motion in the up and down direction. But when we look at how hard that cat was pulling, it had a lot of pull, and it finally overcame the friction of the door. So therefore, once again, this would be the amount of motion that occurred, and since this is the extra amount in the arrow that's moving in this direction, then the overall motion would have been in that direction by this much right here, because that's the amount of difference in the arrows. So therefore, if we were to label this one, this would be an unbalanced free body diagram, and that would mean that there was motion. The cat got free. Meow. All right, so there's the main difference between balanced and unbalanced free body diagrams. Go out there, make some motion.